Between life-friendly worlds and silent, airless ruins drifting through space, there exist the giants, colossal realms shaped by gravity and fire. These are planets so massive they almost became stars. Some could cradle life. Others exist as reminders of how unforgiving the universe truly is. Tonight, we explore both extremes.
Take LHS 1440b, a planet orbiting a small red dwarf about 49 light-years from Earth. Its key stats are striking: around 6.4 times Earth's mass and 1.7 times its radius. A single year there lasts just 24.7 days, as it circles its star at only 14.2 million kilometers. Now imagine standing on its surface. Gravity would feel about twice as strong as on Earth. Every movement would be heavier, slower, more deliberate. This is no fragile world, yet it lies within its star's habitable zone. That's why scientists are intrigued. A planet this massive can retain a thick atmosphere, resisting erosion from stellar winds. It can hold onto its air, and possibly its water. Recent observations even suggest it might contain large amounts of water, perhaps even resembling an ocean world. Its host star also appears unusually calm for a red dwarf, which matters. These stars are often highly active and can strip atmospheres from nearby planets. But here, conditions might be stable enough for something more. And yet, this raises a question. If a planet like this can preserve its atmosphere, how does another, far more massive, lose everything? Imagine Jupiter, but with all its visible layers stripped away. No clouds, no storms, no vast envelope of hydrogen and helium, just the core. That's essentially what we may be seeing with TOI 849b. This planet has about 40 times Earth's mass, yet only 3.4 times its radius. That means extreme density, far beyond typical gas giants. Even more astonishing is its orbit. A full year lasts just 18 hours. It circles its star at only 2.3 million kilometers, an environment of intense radiation. This region is known as the Neptunian desert, where planets of this size are rare because their atmospheres are believed to be stripped away. That's the leading explanation here. The star's radiation likely blasted away its outer layers, exposing what was once hidden deep inside. A planetary core laid bare. We may be observing something we were never meant to see. But what happens when a planet doesn't orbit a star at all? Often shortened to SIMP J01, a free-floating object drifting through interstellar space about 20 light-years away. It exists in the gray area between giant planets and brown dwarfs, with a mass around 12.7 times that of Jupiter. It spins incredibly fast, completing a full rotation every 2.4 hours. For comparison, Jupiter takes about 10 hours and Earth takes 24. Such rapid rotation generates a powerful magnetic field. Observations reveal auroral activity linked to a field strength of about 3.2 kilogauss, thousands of times stronger than Earth's. Despite drifting in darkness, it is far from inactive. The James Webb Space Telescope has captured detailed spectra, using its rotation to map atmospheric changes. This world is alive with complex weather, chemical processes, and heat circulation. It still emits infrared radiation, residual heat from its formation, keeping it dynamic and energetic even in isolation. And finally, we arrive at a true giant. ROXs, 42BB is so massive and distant from its star that it can be directly imaged. It has roughly 9 times Jupiter's mass and orbits at an enormous distance of about 23.5 billion kilometers. One orbit takes nearly 2,000 Earth years. Its temperature is estimated around 2,000 Kelvin, hot enough to glow faintly on its own from leftover formation heat. But here's where planetary physics becomes strange. There's a limit to how large a gas giant can grow. Adding more mass doesn't keep increasing its size indefinitely. Instead, gravity compresses it further, making it denser rather than larger. That's why many gas giants end up with similar radii, despite large differences in mass. ROXs 42. BB sits near the boundary between planets and stars, massive enough to approach stellar conditions, but still not sufficient to ignite hydrogen fusion. Its origin remains uncertain. Did it form within a planetary disk like a typical planet? Or did it collapse directly from gas like a failed star? This is where definitions begin to blur. What truly makes a planet a planet? Is it mass, orbit, formation, history, or simply the fact that gravity held it together without crossing the threshold into becoming a star? The universe is vast, and its giants challenge everything we think we know. Stay curious,